Hello everyone, this is lecture 3 of the computational physics course, and in today's lecture we are going to be discussing statistical models. And if you want to look at some reference for this, I would suggest looking at the book Numerical Recipes. We're going to be discussing some parts of chapter 14 and 15. A lot of what we're going to be discussing is pretty standard statistical textbook stuff. So in principle, you can also pick up any good statistics textbook and follow the relevant discussion from there. Right. This is also linked to the next lecture, lecture 4, in which we'll be talking about Monte Carlo methods, random numerical methods that use random number generators. That also ties up with statistical models and statistical descriptions. So let's get into it. So why do we use statistics? Normally, in most cases, it's because the data that we have is very numerous and we want to make some inferences based on this data. We want to draw some conclusions based on a large amount of data that we have when it is not possible to actually individually look at each number or each piece of data. That's why we tend to do statistics as a way of summarizing the results of that entire vast collection of data. So to give you an example, suppose we were talking about incomes of all people in India. So what you can do is during the census, you can go and take information. So let's say we have what, 1.3 billion citizens. So suppose each citizen has a number, a serial number assigned to them. So 1, 2, 3, and so on, going all the way up to 1.3 billion. And each one has some income, let's say. So this person has certain amount of income. Citizen 2 has a certain amount of income, and so on. So each of these people, you list out all their income. So you have a list of numbers, 1.3 times 10 to the 9 such numbers. Now this is a very detailed level of information, and just by having this list in hand, one can't necessarily draw any major conclusions from it. So, so this description, which is the most detailed description that one can have of a system, is referred to as a micro level description. Micro level or micro state description. There's yet another level of describing the system, which is called the macro level or the macro state description. And in that, what you do is you collect all of these numbers together and get one number out of it. So for example, you might want to ask, what is the average income of a person in India? So if you take average, or you might want to ask, maybe you've done some course in statistics before. You might have seen something called standard deviation. Or median or mode, you might be familiar with these terms. So these are just single numbers which try to give you a sense of the entire set of microstates that you had over here. So this kind of description is called a macro level or a macro state description. And then in between these two levels, there is yet another, there's a third level, which is called a distribution description. In that, what you do is you club all your micro level information into into certain bins. So you can say how many people have income, let's say between 10,000 and 20,000 rupees. How many have income between 20,000 and 30,000? And so on. So you have divided the whole range of possible incomes into individual bins, and you're counting the number of people in each bin. So now what you can do is, on your x-axis you can plot income bins. So 10,000 to 20,000, 20,000 to 30,000, 30,000 to 40,000, and so on. And on the y-axis, you are plotting the number of people who fall in each category. And this number of people is referred to as the frequency. Means how frequently are you finding a person who has income between 20 and 30,000, and so on. So when you make this plot, it's basically a histogram, because you're counting how many times you're getting an income in this range. So you might get something like this, let's say. So you might get some such histogram, and this description as a histogram is called a distribution description. So the distribution description lies in between the micro and the macro level descriptions, because it contains more information than the macro level distribution. Macro level just says what is the average over all of them. It doesn't tell you how those incomes are spread out. On the other hand, it has less information than the micro level description, because in the micro level description you can say, okay, if I ask person number 536 what is their income, then that information is there in this list. But in the distribution description, that information is not there. You have lost the information about individual points of your data set, but what you have is some aggregate description in terms of the range. So how many people have income in this range, how many people have income in this range, so on. So the distribution description has some intermediate level of information, and each of these three levels, macro level, micro level, and distribution level, have their own advantages and disadvantages, and they have their own utility. So uh, depending on what you are trying to do, you might find different levels of the description important for your purposes. Let's take a physics slash chemistry example for this. Suppose I have a container containing some gas. So there are gas molecules inside this. So if I say, suppose there is 1 kilogram of gas, then there is probably going to be Avogadro's number, so 6 times 10 to the 26 molecules inside this. Each of these molecules has a position given by x, y, z, and it has some momentum. So let's call it px, py, pz, or if you prefer velocity, vx, vy, vz. So the micro state description would be, okay, particle number 1, its position vector is given by x, y, z, and its momentum vector is given by vx, vy, vz. Particle number 2, well, so let's call this x1, y1, z1, vx1, vy1, vz1. Then this fellow has coordinates x2, y2, z2, and velocity coordinates vx2, vy2, vz2. And then you keep going this all the way for all your Avogadro's number of molecules. So this one has x, na, y, na, z, na, vx, na, vy, na, vz. So this is your complete description of your system. No more information is possible. You have all the positions and all the velocities of all the particles present over here. But is this going to be useful? If you are trying to find some property of this overall system, so normally what kind of properties are we interested in when we are looking at a gas? We might be interested in the temperature of the gas, or the pressure of the gas, or the density of the gas. So all of these depend on the positions and the velocities of these particles. Uh, so for example, the amount of force that they are applying on the walls of this container will tell you what is the pressure of the gas. Or if you try to find out what is the average kinetic energy of these particles, then all of those will contribute towards what we call the temperature of the gas. So when we are interested not in the individual properties of each and every molecule, but we are interested only in the temperature or the pressure or the density and so on, then what we are doing is we are creating a macro state or a macro level distribution description. So just one number, temperature, that will define the kinetic energy of the system in an aggregate fashion. Only the pressure, that will tell you about the forces being applied. So that is just a one-stop description of your system. So that's the macro state. And then in between the two, you can have a distribution description. Which I don't know if you've studied in your 12th standard, something called the Maxwell-Boltzmann velocity distribution. It basically says if you have a system of an ideal gas like this, then how are the velocities distributed? So will most of them have very small velocities? So will it look something like this? Or will most of them have very high velocities in which it will look something like this? Or are most of them in the middle and then it becomes less on both sides? It turns out that is the correct description. It looks something like this. So, and there's a formula for this. So this is called the Maxwell-Boltzmann velocity distribution. And the mean temperature, the mean velocity over here depends on the molecular weight of the molecules, and it depends on the overall temperature. So this is the distribution description for the system. So like in various statistical systems, you can have a micro level description, a distribution level description, and a macro level description. So what should we look at? Let's look at a few examples of kinds of various shapes of distributions that one might have. And I have taken these examples mostly just not from physics or chemistry, but just from some general everyday situations in case it becomes easier to appreciate. So for example, suppose I'm looking at the distribution of water consumption in India. Well, daily. So per day, how much water are people using? So on the x-axis, suppose I plot number of liters of water used per day, and these are distributions. So on the y-axis, it's always a frequency or the number of people or like a number of something. So this is going to be like a histogram. So what are you expecting? Well, we have a large number of poor people in our country. A lot of them don't have access to water. So I'm guessing most people are going to be in this range where there is very less, few liters of water being used. There are very few of us who have access to 24-hour water supply. So over here, for the large water usage, it's going to be less. So maybe the curve looks something like this. I don't know. So this is the distribution of daily water consumption in India. Of course, in reality, this is going to be a histogram. So I've drawn it as a continuous curve, but actually it is going to look something like this. But you can approximate it roughly to a continuous curve like this. What if I talk about the height of people? So height, let's say in meters, or yeah, meters, sure, and number of people. So most people might have a height of, I don't know, maybe around 160 to 180 centimeters, so 1.6 to 1.8 meters. And then as you go towards smaller heights, you have fewer people. As you go towards larger heights, again, you have fewer people. So most people will have some average height. Fewer people will be quite short or quite tall. So this curve might look like this, where this might be somewhere 160, 170, 180 centimeters. Then what if what about a time distribution? So time of people going to a restaurant. So if you ask a particular restaurant at what time are people mostly going to the restaurant, they will say that most people come around lunchtime and around dinner time. So their distribution might look something like this. So let's say they open sometime in the morning and there's almost no one until lunch. Then it kind of slows down. Then again, people will come around dinner. Then they close again. So their distribution might look something like this. Or age distribution. So in a given country, how many people how many people are of age 31, how many people are of age 32, and so on. So if you look at India has a very large population of young people. So India's distribution looks something like this. However, if you look at a country like France, their population growth isn't quite as large. So their distribution actually looks like this. So we have a lot of young people, not too many old people, and France has a much smoother. It looks almost flat. I don't think it's supposed to be flat, but maybe something like this. So these are some examples of distributions. As you can see, some distributions like this one have a very prominent peak. Some distributions are just, they keep decreasing. Also these. You can also have distributions which increase. Here is an example of a distribution which has two peaks. So you can have all possible shapes of distributions. It's also possible to have what are called uniform distributions, just flat. They don't depend on anything, it's always constant. So you can have various different shapes of distributions. The only constraint let me say something else. So in all of these cases, the distributions that we have written down, they are supposed to be what? They're supposed to be histograms, right? So actually a histogram is a series of bars like this. And if you add up, so let's just take some examples, say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Whatever it is, there's some quantity along the x-axis, and along the y-axis it's the frequency. So if I ask you how many things are there between 1 and 2, then basically you will count this number, right? So you will read off over here. So suppose this was 20. So you will say 20 times you're getting a data point between 1 and 2. 25 times you're getting data point between 2 and 3, and so on. Now, but what happens when these numbers are very large? So right now it's just 20, 30. But if your statistics are very large, then you can approximate this to be a continuous function. And then what happens? Then, because now this is a continuous variable, you can ask what is the probability of finding something between, like how, when you're asking for the frequency, it is basically like asking what is the probability of finding a point between 1 and 2, or what is the probability of finding a point between 2 and 3. That is what this frequency represents. So similarly over here, for the continuous distribution also you can ask what is the probability of finding something between, let's say, x1 and x2. And the answer is basically going to be the area under this curve. So the area under the curve, when you have a continuous distribution, just tells you what is the probability of finding a point between x1 and x2. So these continuous distributions, there's a special name for them. They are called probability density distributions. So if this distribution, if I call it P of x, then what I'm saying is probability of finding a data point between x1 and x2 is this integral. Now, of course, if you take an integral over the entire range, then the total probability has to be 1 always. So of course I'm saying minus infinity to infinity, but it depends on the physical case. So for example, if this was a distribution in time, then there is no negative time, so then you will do from 0 to infinity. Or if it's number of people or height of people or something, then you'll always go from 0 to infinity. So whatever the case may be, when I'm saying minus infinity to infinity, I just mean over the entire possible allowed range. So basically total probability always has to be 1. That we know. So this is the constraint over any probability distribution. So no matter what kind of distribution you might have, whether it's like a following function or it's a rising function up to a certain point, or whether you have something that has a peak in between, everything is okay as long as you make sure that the total area under the curve, which represents the total probability, is equal to 1. So this is called the normalizing condition or the normalization condition. To normalize means to make sure that total is equal to 1. Okay, so we have seen some distributions. Question is, how do you get a distribution? So if I give you data, so by data I mean micro level data, how do you go to a distribution? Because these are two of the three levels. There's micro level, there's distribution, and then there's macro level. So how are you supposed to go from micro data to distribution? It is straightforward. Suppose in your micro data it looks like 1, 2, 3, 4. Let's take our example of the gas molecules. So you have all the way up to Avogadro's number, and each of them, let's just consider the velocity, the magnitude of the velocity. So that's just one number you have, no? Vx square plus Vy square plus Vz square, magnitude of the velocity. So V1, V2, V3, blah blah blah, all the way up to Vna. So question is, how do I make a distribution out of this? So you look at the minimum possible velocity that you can have. So let's call it Vmin. And look at the maximum possible velocity that you have in your list. Let's call that Vmax. And then you divide this up into smaller bins. Similar to what you did when you were doing numerical integration. So divide up this thing into small bins. So you, for example, so this might be between 5 meter per second and 6 meter per second. Then 6 meter per second to 7 meter per second, and so on. And then looking at your micro level data, you just count how many times are you getting between 5 and 6, how many times are you getting between 6 and 7. So when you do that, you are creating a table. So 5 to 6, 6 to 7, 7 to 8, and so on. So these are the velocity bins, and over here you are putting down the frequency. You'll just count in your entire data set how many times do you get between 5 and 6, how many times do you get between 6 and 7, and so on. So you make this kind of a table. This is called a frequency table. And when you're plotting the histogram, what you're actually plotting is the output of this frequency table. And so on. So that's how you go from the micro data to the distribution. And of course, if the number of bins is very large, then you will actually see that this looks kind of like a continuous curve. So that's the relation between micro level and the distribution description.